Hello everyone. Today we are diving into a really fascinating topic in modern cryptography. Something that's not only clever but also a bit sneaky. It's called Honey Encryption, a new way of securing data that doesn't just lock information, it deceives attackers. You see, traditional encryption protects your data by making it unreadable. But Honey Encryption goes one step further. It fights back with fake but believable data. It's a bit like a it's a bit like a digital prank on hackers. They think they have cracked your password or key, but all they have found is a convincing lie. Let's start by understanding the problem. In normal encryption systems, when you use the wrong key, you get random garbage, just meaningless symbols or text. That might sound okay at first. After all, the attacker doesn't get the real message. But the problem is, modern attackers don't guess randomly. They brute force, meaning they try every possible key until the decrypted message makes sense. For example, if the hacker sees decrypted text like FJ32JSLK2, they know it's wrong. But if one of their attempts give a result like transfer $50,000 to account 4590, they immediately know it's the real one. That's the weakness Honey Encryption is designed to fix. Now, why is this such a big deal today? Because brute force attacks have become incredibly fast. In the past, trying every key could take years, even centuries. But now, thanks to powerful GPUs, cloud computing, and botnets, hackers can test millions or even billions of passwords every second. Even strong encryption can be vulnerable if the attacker has unlimited tries and time. So we need smarter systems, not just stronger keys. Honey encryption changes the game by making every decryption look plausible, even when it's totally wrong. So, what exactly is honey encryption? At its core, it's an encryption method that gives fake but realistic outputs when you use the wrong key. Normally, a wrong key gives you gibberish, but with honey encryption, every wrong key produces something that looks real. For example, if the real message was a credit card number, a wrong key might produce another valid looking card number. If it was a password, you might get another password that follows real world patterns. So when a hacker tries to brute force, they get 100 believable results, but they have no idea which one is true. That's the magic of honey encryption. To make this idea easier, imagine a magic safe. You enter a code and the safe always opens. If you enter the correct code, you get the real treasure. If you enter a wrong code, the safe still opens but shows you fake treasure that looks perfectly real. So, if a thief keeps trying different combinations, the safe keeps rewarding them with fake gold, fake diamonds, and fake cash. They'll never know if they have actually found the real one. That's how honey encryption works. It never reveals which key is right. Now, let's get a little technical, but don't worry, I'll keep it simple. Honey encryption is built around something called a distribution transforming encoder or DTE. Here's what the DTE does. It takes real message and maps them to numbers that match how likely certain messages are in real life. Then, during decryption, if someone uses a wrong key, the DTE still produces a message that fits the pattern of what a real message should look like. For example, if your system stores birthday, the DTE knows that valid dates are between 900 and 2025, so even if a wrong key is used, it still produces a realistic date like 15th June 1998. In short, the DTE knows what realistic data looks like. Honey encryption uses that knowledge to fool attackers. Let's see a concrete example. Suppose you are encrypting a credit card number. Now, if an attacker uses the wrong key, instead of getting gibberish, they might get another valid looking number like this, or maybe this. All of these look like valid credit card numbers. So, when the attacker brute forces, they will find dozens of believable results, but they can't tell which one, if any, is real. That's why brute force attacks simply fail. Now you might wonder, where can we actually use this? Let's look at some practical applications. Password managers. If a hacker steals an encrypted password vault, Honey encryption can make every password guess look real. Credit card databases. When wrong keys produce believable numbers, attackers can't extract real credit card info. Secure messaging apps. Fake messages can appear instead of gibberish, confusing anyone trying to intercept communication. Sensitive personal data like medical records, ID databases, or biometric info. In short, it's great for protecting data that's attractive to hackers. There are several benefits to Honey encryption. It completely breaks brute force attacks because every guess gives a valid looking message. It can protect even weak passwords since guessing doesn't reveal the truth. It provides an extra layer of deception, confusing and wasting an attacker's time. It's not just about making encryption stronger, it's about making the attacker's job impossible. Of course, like any system, Honey encryption has its challenges. It needs a realistic probability model, meaning the system must know what valid data looks like. It's still mostly in the research stage, not yet widely adopted in commercial products. If the attacker somehow knows the correct structure of real messages, they might narrow down the possibilities. So, while it's a genius idea, it's not yet a magic bullet. Let's summarize the difference visually. Normal encryption, wrong key gives obvious gibberish, whereas in Honey encryption, wrong key gives fake but believable message. That simple change makes all the difference. One tells the attacker you're wrong, the other makes them think they are right even when they are not. So, where do we go from here? Honey encryption has a lot of future potential, especially in areas like IoT devices, which often have weak or default passwords, cloud storage, where sensitive data from millions of users is stored, financial systems, where fake but plausible transactions can protect real accounts. It can also integrate with AI based security systems where the AI learns what real data looks like and automatically generates fake yet convincing honey data. Let's take a real world style example to make this more fun. Imagine a hacker breaks into a system storing encrypted bank transactions. He decrypts one record and sees transfer rupees 10,000 to account 1234. He smiles thinking he's found the real data. But in reality, Honey encryption has fooled him. That entire transaction was fake. The real one was completely different. So, he is now wasting hours trying to steal fake money from a fake account. That's the genius. Not only does it protect your data, it wastes the attacker's time. Beyond technology, this concept changes the way we think about security. Instead of building taller walls, we can start building smarter traps. Cybersecurity isn't just defense anymore, it's deception. Honey encryption represents a shift from protecting data to confusing attackers. It's like setting up a maze with hundreds of fake exits. The intruder will never find the real door. To sum it all up, Honey Encryption is one of the most creative ideas in modern cryptography. It doesn't just rely on stronger math, it relies on smarter psychology. It tricks attackers into believing lies that looks like truth. As cyber threats continue to evolve, ideas like Honey Encryption will lead the way, not just protecting our secrets, but making those secrets invisible in plain sight. Thank you for listening, and I hope this lecture helped you see cryptography in new, more exciting light. If you have any doubts, do feel free to comment in the comment box below. I would be happy to answer for you.